All right. Hey, everybody. Welcome back to the second lecture on kernel methods for machine learning. Today, we're going to cover these topics: the concept of reproducing kernel Hilbert space, the Moore-Aronszajn theorem, representative theorem, kernel regression. Now, I hopefully you've already taken the first lecture on kernels. Make sure you go over that and really understand it before you move on, because otherwise you're not going to understand anything. So this is a Northeastern University course, and I am Professor Wu. So let's get started. So we previously learned in the last lecture that we can view a function as a point in space. Or other words, you can view a function as a vector. Okay? The reproducing property is another thing we learned. Basically says that the function can be evaluated at x through the inner product of a function as a vector. So we view this function as a vector-esque. And this right here is also vector. So you're taking the inner product of the two vectors. So again, you have the data in the data space. You map it through phi to the function space. So this is phi of x. And then you take the inner product with the function. Okay. Now, the basis functions are the functions here, phi 1, phi 2, phi m. So the collection of basis functions. Now remember, basis function only returns a single value, returns a scalar. However, a collection of them is, let's say there are m of them, there's m dimensions. So phi of x right here is in an m dimension space, okay, because there are m of them. Okay, and a reproducing kernel has the form of kernel multiplying xi, xj, and it's equal to the inner product of phi of xi, phi of xj. So this is basically what we went over last time. And before we move on, just to really make sure you understand these concepts, you need to warm up by answering the following questions. First, if we have two feature maps, they are linear, phi 1 and phi 2. What is the kernel function? The function itself. Okay, so see if you can answer that. Pause the video. Okay, remember the kernel functions defined like this. Second, given three data points, right, x1, x2, x3, three data points, what is the feature map capital Phi of matrix? So what is the phi matrix? Now, next, see if you can find a kernel matrix. Remember that the kernel matrix is essentially the phi matrix times the phi matrix transpose. Okay? Pause the video and we'll go on. Okay? So, for the first question, if the feature map is x and 1, remember it was x and 1, therefore, if you have xi, xj, right, it's just the inner product between them. Xi, xj. Therefore, it's xi times xj plus 1. That's it. This is the equation for the feature map of a linear. And over here, the phi matrix is therefore, let's see, what are the points? So it's 1, 1, 0, right? So x1 is 1, 1, 0, and the feature map is 1, 1, 1. So should be the feature map. And the kernel matrix is the feature map times its transpose. So you just multiply by its transpose, you have the kernel matrix. Okay. Now, the next thing we need to refresh your memory, very important for today's class, is that going back to linear algebra, remember the concept of span. We did this in class several times. The concept of a span giving a set of vectors. You have a vector this way and a vector this way. Therefore, the span is anywhere in this 2D plane. And in this 2D plane, is every single point that's reachable by this. So the span of a set of vectors is defined by the basis vectors. So these are the basis vectors. All the possible points reachable by some combination of the basis vectors. By stretching or shrinking the combination of basis vectors, you can reach multiple points. So all the possible points you can reach. Okay. So for example, let's say given that we have two basis vectors, these are the two, and can we reach these targets? So 3, 2. Can we reach 3, 2? Yes. If we stretch the first target vector by 2 and then keep the second vector, then we can reach 3, 2. Another example, 1, 0. Yes. If we just zero out the first one and multiply the second one, we can get 1, 0. Same idea. Can we get 2, 1? Yes. You just add the two of them and you get 2, 1. So all these 3 points are reachable by the basis. So let's extend this idea to the span to function space. Now remember, we're saying that a function, now we can visualize a function as a point in space, a vector, right? So given the feature map XAB, now let's say we have the feature map. The first feature map is we extract the A. The second one, we extract the B. And the third one, we just set it to 1. Therefore, the feature map looks like this. Now, given 2 points, x1, x2, these are the 2 points. These 2 points, when mapped to RKHS, they become 2 functions. So 2 points, 2 data points, when you map them to RKHS, remember this is equal to phi x1, phi x2, right? Once you map 2 points into the function space, RKHS, these 2 points are now functions, function 1, function 2. And these two are vectors. Remember, functions in RKHS are vectors. Now, therefore, they also create a span, right? These two functions will create a span. So given these 2 points, x1, x2, and to create 2 functions within RKHS, see if you can find if f, another function, f right here, is within the span of these 2 functions. Okay? In other words, is there alpha beta such that you multiply alpha by the first function and beta by the second, you can get to this function right here. So pause the video. Let's see if you can do it. Okay, we're going to move on. Okay, so the first point, if we plug into the feature map, it will be 1, 3, 1. Okay, hopefully you got that. 1, 3, 1, because it's just AB1, AB1. The second one is 2, 2, 1. So hopefully you got that. And notice that if you use 2 times the first one plus 1 times the second one, it gives us the third one. So yes, this is within the span, Okay? Okay, now I think we're now ready to move on. We previously learned that the feature map maps the data from the data space to the function space, right? So here I keep drawing the same picture. So it maps the data from the data space to a function space. And over here is a function. This notation says that it's a function such that it maps the data from the data space to the function space. That's what this notation says. Okay. Depending on the number of basis functions, we can get RKHS of various dimensions, right? So depending on the different bases. So in the plot below, if our basis is just x phi 1, phi 2, right? That's 2. That will basically form this 2D plane. Okay? We have a 2D plane. However, if we have 3 basis functions, 1, 2, 3, now we have added extra dimension. So if we have a point P, right, the 2D plane can never ever reach the point P. The closest you'll ever get is still on the plane, and you're always going to have some kind of error, right? If you're trying to reach P, right, you can never ever reach P, right? So, so in 2D and 3D, obviously we can visualize them. We can visualize a 2D plane. We can visualize the 3D space. However, it's much, much harder to identify and quantify this function space once it gets to higher dimension, 4, 5, 6. So how do we mathematically then, like if we can't visualize them, how do we use mathematics to help us conceptualize this space, right? How do we conceptualize this space, right? So there are two guys, Moore and Aronszajn, basically answer this question for us. Okay? The Moore-Aronszajn theorem basically says that first thing it says is every positive kernel. So kernel is a function that takes two data points from the data space, right? Two points in data space and returns a number, a positive, a number. And so the first thing it's saying is that every single kernel, as soon as you define a kernel function, right? If this is a kernel function, you automatically can associate this with a unique function space of RKHS. So as soon as you define a kernel, it implies that there is a RKHS function space. This function space is unique to this. In other words, if you have another kernel that is slightly different, kernel 2, xi, xj, slightly different, then its associated RKS will definitely be different. This will be associated with this, and this will be associated to this. And the two are not equal, right? So this means that this has unique, the word is unique, uniquely defines one, and the second kernel uniquely defines yet a different one. So every kernel function will uniquely define a different space of functions, okay? Which makes sense. You have a different function, then obviously it's defining a different function space. Okay, the second thing you want to take away from the Moore-Aronszajn theorem is that the space spanned by all the samples in the RKHS is the RKHS. Okay, so what I mean by that is, let's say you have a space, the data space. So now within the data space, there are infinite points, x1, x2. There's infinite points in this data space. Now, if you map every one of these points, infinite points, to the function space, so you end up with phi x1, phi x2, all the way to phi x infinity. So they're infinite points. The span of these points is the RKHS. RKHS. So this is how you can mathematically visualize this function space. It starts from the data space. From the data space, you map every single point here. So now you have lots and lots of vectors. The span of those vectors describe the size and magnitude of the RKHS. It describes basically what this function space is like. So again, every single point here. Okay. So that's what it's basically saying. And it's also saying that within this space, the concept of inner product is defined as this. But this is a little complicated. Don't worry about it. The way I taught you of how inner product works is the way you can kind of visualize how it works. So there are basically three things. Every single kernel is associated with its own RKHS function space. Second, Moore-Aronszajn tells us how to visualize this function space. Basically, we take every single data from the data space, map it to the function space, so you have lots and lots of vectors. The spans of those vectors is what quantifies the RKHS. Okay? Now, here it calls a pre-RKHS in the theorem, but for our purpose, don't worry about the difference between pre-RKHS and RKHS. Just treat them exactly the same. Don't worry about that. Okay? Now, this theorem is really, really foundational. This is a foundational theorem that basically explains why so many things work. And this theorem is so foundational, if you don't understand this, a lot of things later also won't make sense. Okay? So draw the visualization. I kind of did that already. Moore-Aronszajn theorem in real life. So in Moore-Aronszajn theorem basically says that if you need to have infinite, right? So over here you have infinite points. And then you have to map every infinite point into RHS. But in real life, you don't have infinite. You only have n samples. So x1, x2, all the way to xn. So the n samples is kind of like a representative of the entire space. Since you don't have infinite of them, n of them is the best you can achieve. Therefore, RKHS, given only n samples, you will map the n samples, phi of x1, phi of x2, all the way to phi of xn, right? The span of this phi of x1, phi of xn, the span of this is the best way, given the data you have, you can describe the function space. Okay, so this is the span. So you have the theoretical RKHS, which will require you to have every single possible point. However, in real life, you don't have every possible point. You only have n. Therefore, in real life, the span of only n samples is the best you can achieve. Like you can't really get anything outside of those n samples. Okay. So therefore, in other words, every single function in RKHS. Remember, every point in RKHS is a function. So every single function in the entire RKHS can be approximated by the linear combination of your points. So if you take all your points, 1 to n points, and then some combination of them will reach every single function in this space, right? Given some appropriate set of coefficients, right? So we can simplify this expression by pulling out all the alpha. So it's alpha times this. And remember, the phi matrix that we always worked on looked like this. And therefore, this right here is just a phi transpose. And simplifying this further, every single function can be represented as phi transpose times alpha. Okay. Now this theorem it's really has some very significant and subtle implications. We have n data points, right? In your data set, you have n of them, and the n that forms n functions inside RKHS. So these are n functions. Since the entire function space is spanned by these n functions, every single function in the RKHS is reachable by using your data. So your data allows you to reach every single possible function in the entire space, given some combination of alpha. Okay, that is what this is saying. It's saying that just by using your own data itself, it creates a bunch of functions, and those combination of functions allows you to reach any function in the entire space. Okay. Therefore, if every single function can be reached using your data, the optimum function for any minimization problem. Remember, when we are doing minimization problem, we are finding the optimal function, right? So the optimum solution function is part of every function, right? If you have every function, the optimal one must be inside the every function. So the optimal solution must also be a combination and must also look like this. So this is magical because it tells you that we know what the optimal solution look like already, which makes life a lot easier in many instances. Okay. Now, the implication of Moore-Aronszajn. If every single function in it can be represented in this form, it implies that any minimization problem, if you have a minimization problem and you're trying to find a function, right, that minimizes some kind of loss function, like you want to minimize the average error, you want to minimize the cross entropy, whatever, that function, we'll call it the optimum function, we'll call that f star, right, must be within the hypothesis space of RKHS. And the Moore-Aronszajn theorem tells us that that optimal function must look like this. So as long as you know alpha, you know the optimum function. Right? This is very useful because this implies that we know what the solution is supposed to look like already. And we simply need to find alpha values. Now, we have seen this before, right? In regression, that was exactly what happened. In regression, we formed this 5 matrix and we want to find the weights, right? Now, instead of finding the weights, now in kernels, you want to find the coefficients, and they're different. The weights and the alphas are different. Okay, so this leads everything I just talked about leads us to why representative theorem work. The representative theorem basically says that the optimal solution for these kind of minimization problems has to look like this. And well, I'm missing a transpose. Has to look like this. And this right here, it was basically the intuition of why this works is like what I just explained to you. Okay. So the representative theorem um, um, formally declares the optimal solution to look like this. Okay. So that's the representative theorem. Okay. Now let's take a step back and go back to our regression. And we're going to add some kernel flavor into regression. So remember, in regression, we were trying to find a function such that if we plug in the first x, it will predict the first label y1. If we plug x2, it's going to predict y2, right? And we didn't know what x is. So what we did is we form a set of functions, and then we want to find the weights. This is regression. And once we find the weights, ideally, when we plug x1, we're going to predict y1. When we plug x2, we'll predict y2. Okay. Now, we can write this into the matrix format by pulling out w1, w2 here. And this right here is just a big 5 matrix. This is W. So this is what we were trying to solve when we're solving regression, right? Now, let's do exactly the same thing, but this time change our perspective from the kernel perspective. So from a kernel perspective, well, we start off with the same problem we're trying to solve. Now, F right here, well, there's this thing called the reproducing property. So F is simply equal to this from the reproducing property. So F1, F2, F3, so we can replace this with this due to the reproducing property. Now, F is all the same, so we can pull F out. So now we have F. So what happened is this is also the 5 matrix. So they basically look identical. The only difference is that we are now interpreting the coefficients, the weights, as a function, because that's the whole point. By knowing the weights, we basically know the function. Is that oh, if that's the only case, it doesn't feel like kernels has really given us anything. Like we like what if this interpretation change is all we got. However, that is not it. We actually got a lot more than this. At first glance, it may appear that we arrive at basically the exact same conclusion. However, no. After what we learned today, the difference is that we learn that the optimal solution F has to look like this from the Moore-Aronszajn theorem and the representative theorem. By knowing that, we can plug this into F because we know what the optimal solution is. So now this is what we're trying to solve from this, right? We're trying to solve this. Now we do know what the optimal is. We just plug the optimal in. Now remember, when you have phi times phi transpose, that is a kernel matrix. So here we have alpha times the kernel matrix is equal to y. So and this right here is called the kernel regression. So in basic linear regression, we're trying to solve this. In kernel regression, we're trying to solve this. Okay, so these two are the difference. Now, the formula seems different, right? But but when we actually solve them, and then once we solve for alpha, we can solve for the function f or w. You're going to get exactly the same result. You're going to get w and w here. You use the closed form solution, or you solve it this way. You're going to get exactly the same thing. So if we did all that work just to get the same answer. Why in the world did we want to learn the kernel method? Right? It seems like a lot of work and very little benefit. Well, both methods will solve linear regression and both will give you the same result. Okay? Therefore, it's very it's then you want to ask, like, okay, if we get the same result in the end, what the hell is the point? Well, let's take a look. Let's take a look at the various kernels we have. So the one we just did is a linear kernel. Okay, this is a linear kernel. We just did this. It only has two bases, right? Two bases, and then we have some of us, well, most of us probably have done the polynomial kernel. The polynomial feature map. Well, let's see, two, three, four, five, six. There's six of them. So this is more powerful than this because, well, this is a much larger RKHS, right? So this is a much larger function space. So you can fit many more kind of functions. Okay, okay. So the kernel function looks like this for a linear, and the kernel function for this, when you take the inner product, will look like this. So this is the kernel function. Now let's look at a different one, Gaussian kernel. Well, Gaussian kernel has, wait a second, it has one, two, three, four, five, infinite. So a Gaussian kernel has infinite basis functions. Okay. So can you calculate infinite basis functions? What are you going to do? You're going to take your data and plug it into infinite of them, right? So, however, you can't calculate the feature map. Feature map cross. Can't do it. However, look at the kernel function. The kernel function itself is pretty easy to calculate. Okay, keep that in mind. Keep that in mind. You cannot calculate infinite, right? So if you have a case where you want to have infinite power because you have infinite functions to do whatever you want, you cannot have infinite bases. However, you can calculate the kernel function. That is the point you want to remember. You may not calculate infinity, but you can obtain the power of infinity by simply calculating the kernel function. Okay? All right. So the key point here is notice that while some feature maps are easily calculable, the Gaussian has infinite number of feature maps. I mean basis functions. So the feature maps is infinite dimension, giving you infinite power. This is very powerful, but obviously you can't calculate infinite basis functions. And notice that while the feature maps are impossible to obtain, the kernel function is relatively easy to calculate. Okay? That is the key point here. So over here, let's say let's use the infinite basis. We have the Gaussian with the infinite basis. See how the feature map has infinite bases. So it's obviously we can calculate the feature map. So if we look at this perspective, this is impossible because it's going to be phi is going to be an n by infinity matrix. W equals to y, right? Because the width depends on the number of basis functions you have. So if you have infinite basis function, this is going to be infinite. And obviously, you're not going to be able to calculate infinite w, right? If w is infinitely long. So that's not doable. So at a first glance, here, trying to solve it the traditional machine learning way with regression, you have limited capability of how many basis functions you can use. But if you use Kernels, remember, the definition of a kernel function is k11. So you just plug this in. So this has n rows and n columns. So while this is infinite, this is n by n. So the kernel matrix is calculable. So you can obtain this by just calculating the one at a time. Once you calculate this, this is an n by n matrix. This is alpha. We know how to solve this kind of problem already, right? We can use the closed form solution to solve this. What we have done is we have obtained infinite power at the cost of an n by n matrix. That is why using kernels is useful. Obviously, if you just use a linear feature map over here, that you're not going to gain anything because you can just calculate a linear feature map outright. But if you want to gain infinite power, then you would need to rewrite the same equation in this formulation. Okay? So the use of kernel matrix instead of feature map to avoid dealing with infinite dimension. Doing this whole process is called a kernel trick. It's a trick that essentially converts infinite dimension into a feasible n by n matrix. By applying the kernel matrix, we gain the power to leverage infinite basis functions without infinite calculation. The cool thing about this, once you have this formulation, depending on the situation, this formulation stays the same. You can just pick a different kernel function and calculate a different kernel matrix. And then you can solve this again, right? There are many, many different kernel functions. You just pick one, pick a powerful one, pick a less powerful one, and this formulation will not change. Okay? So okay, now that you get alpha, let's say now that we got alpha, what do we do with it? Well, remember that the optimal solution is phi times alpha, right? And what is phi? Well, phi is the feature map of the first sample, second sample, all the way to the end sample. So wait a second. Well, if we're talking about Gaussian kernel, the feature map's infinite. So this right here is infinite long. So it's every one of them. So even if you have alpha, well, you still can't calculate this thing. So like, how is that useful? Right? Like, what do you do then? Like, you cannot obtain this function because these are infinitely long. True, you can't do that. However, most of the time, you don't you don't need five. You don't need to get the function itself as a vector. Most of the time, you don't. What you care about is phi of x with x. You care about what happens when you put a value inside this function, and this we can calculate. Okay, so let's see how that is done. So remember, let's say that we did obtain our best result. And from the reproducing property, we know that phi star of x is just equal to this. So if we want to put a value in, it's just equal to this. Now, this is inner product. We can transform that into a dot product. So it's just this vector dot this vector, right? Now, if we look at it this way, what was this? Well, the optimal solution is this form, right? Phi transpose alpha. And now we solved this, so we do know alpha. Okay? And the problem was we couldn't really calculate this. Okay? Now, let's write this out. So alpha, and this right here is phi 1, phi 2, all the way to phi xn. Well, we can multiply this with each one of them. That we can do. When we multiply them, it's the inner product. And this right here is the definition of a kernel with x times x1, x times x2, right? X times x2. So this right here is the definition of kernel times the alpha. Therefore, if you're trying to evaluate x, all you have to do is pass x into a kernel. and then add up all the kernel values. You know how to calculate the kernel value. So you loop through every single n samples and multiply them by alpha I, alpha 1, alpha 2, alpha 3, right? And therefore, you can, even though you can't get the phi, even though you can't get the phi, you could, however, get f of x. So you can evaluate the result at any x through this formulation. Okay? From this observation, we conclude that the optimal solution at x is simply you put x here and loop it through the kernel function for every n samples multiplied by alpha. And after regression, you know what the alpha value is, you know what xi is because those are your data, and you just put x in, right? Notice how this looks almost identical to kernel density estimation we learned previously, right? Basically, the kernel density estimate came from this idea, and a lot of kernel methods comes from this idea. Okay, now that we've gone through this, I want you to answer these questions to really help you consolidate everything we've learned. I want you to write down your own words intuitively what the Moore-Aronszajn theorem is really saying. Okay, and then try to follow the logic of how Moore-Aronszajn theorem leads to the representative theorem. Like I want you to write this logic out. You wanna slowly think through what Moore-Aronszajn is telling us, and then how that leads to the representative theorem. Okay. Then I want you to write a mathematical derivation that goes from regular regression to kernel regression. So I want you to think very carefully how regular regression works, and then how kernel regression, when applied representative theorem, works. And then think about how, by transforming your understanding to kernel regression, allows you to gain infinite power. Okay. Like try to do this without looking at the slide. Like just try to go through the logic in your head slowly, and then write out the mathematical derivation, all right, of this using kernels. Right. Again, try to do all these without, like, try to logically think through it. Right. If you're stuck, obviously, then go look at the slides. But the key is for you to go through the exercise of pretending you're the inventor of all these, and that all of these are logically explained if you can follow the story along. Okay. All right. Now, what's happening when we map data? So when we are mapping the data to this RKHS, what's happening is that we are bending the space. So, like, you may have heard of bending the space in space time. When we are applying the feature map, right, and then we go from the data matrix to the phi, right? In the phi, remember, we're still running linear regression, everything the same. So in phi, it looks like a line. So in the RKHS, it looks like a line. However, in the original space, you bend the space. So we're going to see this bending of space a lot later on as we move on. Okay. So, like I said, while the line is straight, you're running a linear regression in RKHS. However, the original space is now warped and bent. Therefore, what looks like a straight line in RKHS is actually a curve in the original space. So this, you're learning how to, like, bending space and time, essentially. The bending of space via feature map is how we can turn lines of various linear models into curved models. So when you're running regression, right, linear regression, you can only get a line, right? However, because you're bending the space, you're able to get curves now. And when you use a Gaussian kernel, you can basically achieve any curve. Okay? The process of kernelizing model is really simple, right? So most of the time what we do is we map the data into a feature map, right? That's the first step. We map the data from the original space into the function space. We map all the points here. And then once we have the points, we realize that the optimal solution is always in the form of phi transpose alpha. That's from the representative theorem. Okay, if you know that, then Then you can then apply this logic and kernelize it. So very often you just convert it into a kernel, because without the kernel trick, you can't calculate infinite dimension stuff. Okay. Now I wrote the code for you guys for this is the I think this is the stock prediction one, the data set. I wrote the code for you. This is kernel regression, but I really don't want you to look at it. I want you to try yourself first. So give this a try. See if you are able to make the predictions yourself, without looking at my code. I provide the code in case for you to study it, but you will be robbing yourself of the opportunity to think this through. And thinking through is the key to learning. Okay, so this is the second lecture on kernels. We're going to move on later. I hope you this will take a couple times, so you need to study this and to let it sink in. All right, I'll see you in the next lecture.